Okay, our problem today is our two problems. The first one is how to show a right triangle in a complex plane. For example, we have the 3 points A, B, and C of respective of fixes as shown. And the problem is show that ABC is a right triangle. It could ask the question in two different ways. First way, find ZB minus ZA over ZC minus ZA. ZBI minus ZA2 minus I over ZC3 minus ZA2 minus I. We will obtain minus 2 minus I plus 2I over 3 minus 2 1 plus I. If you have to find the algebraic form, you can find it using calculator. Mode 2 fraction minus 2 plus 2I over 1 plus I, and the answer is 2I. If he said deduce the nature of the triangle ABC, or deduce that ABC is a right triangle, you should use argument of ZB minus ZA over ZC minus ZA equal argument of 2I, of course, modulus 2 pi. So argument of a fraction equal argument of the numerator, which is the angle that U makes with the vector AB, argument of ZAB, it's the angle that U makes with the vector AB, minus argument of the denominator ZAC is the angle that U makes with the vector AC. Argument of 2I, because of a pure imaginary positive number, so it's pi over 2, modulus 2 pi. According to Grotesco's rule, UAB minus UAC is ACAB equal pi over 2 modulus 2 pi. So the angle between AC and AB is a pi over 2, 90. So ABC right triangle at A. Another method you can show it using the scalar product, but the scalar product you can't use it if you have this method is using the argument. The scalar product you can use it if the question is deduce. If he asks show that ABC right triangle at A, you could find the coordinates of the vector AB. A is 2 minus 1, B is 0 1. So the vector AB has a coordinates xb minus xa minus 2, yb minus ya2, and C is 3 0. So the vector AC has as coordinates 1 and 1. If you did calculate AB dot AC as a scalar product in a plane x prime plus y prime, the answer will be minus 2 plus 2 equal to 0. So the two vectors are perpendicular. So ABC right triangle at A. Okay. Of course, there is another method using the converse of Pythagoras theorem. The second problem of our video today is how to show collinear points. Also, we have two different way of questions or two different way of solving. If you ask firstly, we have the points A, B, and C. If you ask firstly to show that, to find ZC minus ZA over ZB minus ZA in the algebraic form, we will have minus 1 plus I minus 1 plus 3I over 2I minus 1 plus 3I. We will obtain minus 1 minus 1 minus 2I minus 3I minus 2I over minus 1 2I minus 3I minus I. The answer, of course, is 2. If you can find it using calculator. If he said deduce that A, B, and C are collinear, you can use argument of the fraction ZC minus ZA over ZB minus ZA equal argument of 2, of course, modulus 2 pi. So argument of a fraction equal argument of the numerator ZBC or ZAC this is A, ZAC minus argument of the denominator ZAB equal argument of 2. Argument of any positive real number is 0, modulus 2 pi. So this is the angle that U makes with AC, and this is the angle that U makes with AB vector equal 0 modulus 2 pi. According to Chase's rule, the angle ABAC equal 0 modulus 2 pi. Since the angle between the two vectors is 0 and they have A as a common point, so the 3 points are collinear. Second method, using vectors, but this case is not introduced when he asks, show that A, B, and C collinear. Very simply, we can also find the coordinates of the vectors. طبعا A1 3, B0 2. So the coordinates of the vector AB are -1 1, and C is -1 1. So the coordinates of the vector AC are -2 -2, right? Coordinates of the vector AC -1 minus AC -1 -1 -2 1. Okay, AB AB في غلط بالAB. AB -1 -1. If you did calculate x over x prime, you will find -1 over -2 equal half. Y over y prime equal -1 over -2 equal also half. So the two vectors AB and AC are collinear with a common point. So the points A, B, and C are collinear. Why we have to say that A is a common point? Because if they don't have a common point, they could be parallel. So since they have a common point, so the 3 points are on the same straight line, so they are collinear. And that's it all.